Welcome to Part A of Unit 2 for our course on statistics. And for Unit 2, we're going to talk about two different topics. These are really two totally separate topics. The first one will have to do with effect sizes, and the second topic will have to do with error. Or more specifically, it will have to do with different types of distributions that pertain to types of error. And these are really two totally separate topics, but they are both foundational topics. So in Unit 2, we're going to be talking about really important concepts that are foundational to understanding statistics and data analysis. So first, let's talk about effect size. Recall that this was one of the important questions that we can address in data analysis. Recall from Unit 1, we were talking about Moniz and his research on lobotomies, and we were talking about all the important questions we could address if he had quantified his observations. And we said, well, one of the things he could have done is he could have done a clinical trial. And I gave you this example here. So this is the same slide we saw before, where I said maybe we had a treatment group that received lobotomies, and what if the mean outcome on the brief psychiatric rating scale for this group was a 39, and we had a control group that received no treatment, and their mean on the psychiatric rating scale was a 45. So that meant that our treatment group was 6 points lower than the control group in terms of symptoms, so they were better off in this hypothetical study. And the question was, well, how big of an effect is this? Is a 6-point difference between these two groups, is that a small difference or a big difference? And how do we decide? And that's the question of effect size. Now, of course, no one today is going to be doing research trying to test the effectiveness of lobotomies. So here is an example that might be typical of current research. So say we have a researcher, and this researcher is wanting to test the effectiveness of cognitive therapy for depression. There's a common type of psychotherapy where clients are taught to recognize thought patterns that make them depressed and to develop ways of changing those maladaptive thought patterns. And a researcher wants to test the extent to which cognitive therapy for depression is effective. So the researcher would conduct a clinical trial, that is an experiment, where we get a sample of people who are experiencing depression, and some of those people are randomly assigned to a treatment group and they receive cognitive therapy for depression, and other people are randomly assigned to a control group and they received no treatment. And then at the end of the study, we assess their levels of depression. One common way to assess depression is to use an instrument called the Beck Depression Inventory, which is a questionnaire. It has several questions on it that ask about different types of depressed feelings, and people rate the extent to which they feel depressed on the Beck Depression Inventory. So say we do our study, and after our study, the control group, their score on the Beck Depression Inventory, their mean, X bar for the control group is 26.5, and the mean for the treatment group is 17.0. And there's actually been several studies looking at cognitive therapy for depression. And if you did a study, this is actually typical of what these studies have often found. They've often found means in the range of what I'm showing you right here on the page now. And so the difference between these two groups is a difference of almost 10 points, 9.5 points difference between these two groups. That is 26.5 minus 17.2. That's a 9.5 difference between the two groups. And higher scores mean people would be more depressed. So the control group is more depressed. They have a higher score. The treatment group is less depressed. They have a lower score. So we have a 9-point difference between the two groups. And now we have our key question. Well, how big is this effect? Is a 9-point difference a big difference? Or is this a trivial small difference? Is this something to be really excited about? Or is this something that makes us go, oh, that's not very big. I was hoping for a bigger difference. How big is this difference? And how do we go about deciding how big that difference is? And by the way, one clue is that it's going to involve something about measuring things with standard deviations. And here's another example that illustrates the importance of the question, how big is the effect? That is the question of effect size. And this example will come from process research in psychotherapy. That is, research seeking to understand what processes occurring during psychotherapy are predictive of outcomes to therapy. And one of the ideas within process research and psychotherapy is the idea that therapeutic alliance is very important. That is, it's important for a clinician to establish a strong alliance with a client. And so a strong alliance would occur, for example, if a client thought, I like my psychotherapist and we work well together as a team and we're working towards the same goals and I trust my therapist and I have confidence in my therapist, that would be an example of a strong alliance. So the idea is that if a therapist establishes a strong alliance with a client, the stronger the alliance, the better the outcome. So we could attest this in a study. This would not be a clinical trial. This would actually be a type of correlational research where we get a sample of people, and maybe get a sample of people who are all experiencing depression. And I have these people here. It's kind of silly names here. I didn't come up with these names. Got them someplace else. But we have Billy Aiken, Opalese, and Momentum, and Deirdre Oppings, and Call It Even, and Three's a Crowd. So we've got these 6 people here, and maybe they're all experiencing depression. And what we're going to do, they're all going to begin psychotherapy with a therapist. And at the beginning of their therapy, we're going to get a rating. Maybe we'll give them a questionnaire and ask them to rate the quality of their alliance with their therapist. And so Billy Aiken, his alliance score is an 8. And then Opalese, her alliance score is 14 and a 15. Deirdre Opping, she had a very poor alliance down at a 2, but Call It Even had very high alliance at an 18. So each person rates the extent to which they feel a strong alliance with their therapist. And then at the end of their therapy, or maybe after a few months or something, we give them that same Beck depression inventory I mentioned to rate their levels of depression, and we get their score of depression. And so now we have this data here, and we want to know to what extent is there an association between alliance and depression. And just by looking at these numbers, it's kind of hard to figure out, well, what's the strength of relationship here? Should we look at this and say, oh, there's a very, very strong association based on these numbers? Does this look like a really strong association between alliance and depression? Or does this look like a weak association? And how would we figure this out? And this is a slightly different question from the previous one, but it will actually turn out that standard deviations will play a role in answering this question as well. Now, one of the key things that I hope you learn from this class is the extent to which the question of effect size is important and the extent to which people often ignore that question and don't talk about it. By the time you're done with this class, I hope you're very aware about how important it is to address the question of effect size, and I hope you also become very sensitive to the extent to which this question is often ignored and not discussed. So the question of effect size has to do with magnitude of effect. It's often the key reason for doing a study. It's the crucial thing we want to know when I do a research study. So if I test a treatment for depression, my key question is, how effective is my treatment? To what extent is it effective? What is the size of the effect of this treatment? Or if I want to know what is the association between therapeutic alliance and treatment outcomes, the question is, what is the strength of that association? To what extent is there a relationship between those two variables? And note that when I'm talking about effect size, I'm talking about something that's on a continuum. How big is this effect? Something that could be trivial, big, small, medium. To what extent is there an effect? It's not a question that could be addressed in a yes-no type of format. So if I ask a question like yes-no, then I'm not talking about effect sizes. So the way that research is often talked about is in this yes-no format. And when we talk about research this way, we're not talking about effect size. So for example, if I say I did a study testing a treatment for depression, and I discovered there was an effect. Well, if I say it that way, I'm talking like either yes, no, there was an effect, or there wasn't an effect. That's a kind of dichotomous decision, and that doesn't tell me any information about effect size. That doesn't tell me how effective the treatment was. It's just some kind of dichotomous conclusion about yes or no, was the effect present or detectable. And essentially what you're saying there is, if you say there was an effect, you're saying the effect was not zero. So if you say there was an effect, you're essentially saying there was some non-zero effect that was detected. Or if I say I do a study and there was a correlation, you're essentially saying there was some kind of non-zero correlation that was detected. Or if you say I did a study with a treatment group and a control group and there was a difference between groups, you're just saying there was some kind of non-zero difference between groups. Or if I say I did a study to test the effectiveness of my treatment for depression and my study concluded the treatment was effective, again, you're just saying there was some kind of non-zero level of effectiveness, but you're not telling me anything about how effective it was. You're giving me this yes-no type of thing that doesn't tell me the size of the effect. I have down here that effect size cannot be answered yes or no. And anytime we're talking about results from research in this kind of yes-no dichotomous format, we are ignoring the question of effect size. Notably, in a little bit later on in this course, we're going to talk about something called significance and doing significance testing. And we're going to do this. This will be very important. But it's important to note that significance testing will not be something that's addressing the topic of effect size. We'll talk about this later, but for now, just note that significance testing is not effect size. What I'm going to talk about later is significance is something we do to determine if we had a big enough sample to determine that the effect was not zero. And significance is something we talk about in a yes-no format. So if I say something is significant, that means I had a big enough sample to detect a non-zero effect. And if I say something was not significant, that means my sample was not big enough to detect an effect. That actually is going to pertain to that issue of can these results be explained by chance? That's going to be a type of inferential statistic. And we'll be talking about that later. But right now, note that significance is not telling us anything about effect size. But when people report results from research studies, they often focus on this issue of significance and report things in this yes-no format. So they would say, yes, it was significant, meaning we've detected an effect, but they don't tell you anything about how big that effect was. So when we're talking about effect size, it needs to be something that's going to be on a continuum, a range from high to low. To what extent is something effective? And anytime we're talking about research results that goes down to some kind of dichotomous yes-no, there was an effect present or there wasn't an effect, well, at that point, we're not saying anything about effect size. And if you start looking at how research is presented in the media, in textbooks, and even in a lot of journal articles, that it's often presented in a way with this yes-no format. I have research results in the media and in textbooks. This is how it's often presented, as there was an effect, there was a correlation, there was a difference, the treatment was effective, and they often say nothing at all about how big the effect was. But that's a crucial question. That's the whole reason why we were doing the research study in the first place, was to determine the size of the effect. And this question of effect size is especially important for clinical psychologists or anyone who's in a helping profession, anyone who's in medical practice, anyone who's giving treatments to patients or clients. Because anyone who's giving treatments to patients or clients, it's important to know the effect sizes of the treatments that you're giving. If you simply know that, well, this treatment has been found to be effective in research, that's just saying the effect is not zero, and that doesn't tell you anything about the extent to which your treatment is effective. And so if you're going to give a treatment to a patient or to a client, it's important to know not simply, well, the effect of this treatment is not zero. That doesn't tell me a whole lot. What I want to know is, well, to what extent is this treatment effective? How effective is it? And this is also important for getting informed consent to treatments. Part of ethical practice is to get informed consent from clients or patients before they're given treatments. And I would ask the question, can a client or a patient give informed consent if they don't understand the effect size of that treatment? If they're just told, well, research finds this treatment is effective, but not told how effective it is, can they really give informed consent to that treatment? So I would say this issue of effect size is important. Well, it's important for all types of research. It's like I said, it's the primary reason why we do research is to determine effect sizes. And it's also especially important for anyone who's a clinical psychologist or in medical practice or in a helping profession who's giving treatments of some kind to patients or clients, because we want to know how effective those treatments are, both so we can make decisions about what treatments to give to clients and so that we can get informed consent from clients. Okay, now that I've talked about the importance of calculating effect sizes, let's look at how we can actually do that. So what I'm going to do now is I'm going to show you two different methods that we can use for calculating an effect size. There's actually several other methods that we could use to calculate effect size, but the two methods I'm going to show you now are probably the two most important methods for calculating effect size and the two most common methods for calculating effect size. One of these methods is to calculate something called a d-statistic. It's often symbolized with just the letter D here. I got the letter D. And the other method will be to calculate a correlation. And for whatever reason, a correlation is usually, we give the letter R, lowercase r, is the symbol for a correlation. So a correlation symbolized by lowercase r, or a d-statistic symbolized by the letter D, these are the two primary ways of calculating effect sizes. So let's see how we can calculate a d-statistic and how we calculate a correlation. So first, let's start with a d-statistic. Now, a d-statistic and a correlation are actually interchangeable with each other. There's actually formulas that you could use to transform a d into a correlation, and there's formulas you could use to transform a correlation into a d. So they're interchangeable, but there are certain situations where a d-statistic is the most sensible statistic to use for an effect size, and other situations where the correlation is the most sensible statistic to use as an effect size. And a d-statistic is most sensible to use in a situation where you have one dichotomous variable and one numerically scaled variable. A good example of this would be if you're doing a clinical trial or an experiment where you have a treatment group and a control group. So you have two groups, that's your dichotomous variable, is you have a grouping variable. People are assigned to a treatment group or a control group. And then your outcome would be a numerically scaled variable. Say it's levels of depression or levels of psychiatric symptoms or something like that. So if you have one dichotomous variable, that is you have two groups, and you're looking for differences between those two groups on some numerically scaled variable, then a d-statistic is the most sensible statistic to use to report your effect size. And I have the formula for a d-statistic over here on the left, and it is this. We take the mean for group 1, so I need to have two groups. I have the mean for group 1, and I subtract from it the mean for group 2, so I get a difference between the two means, and then I divide that by a standard deviation. I have here, I call it the pooled standard deviation. I'll explain what I mean by pooled in just a moment here. For now, you can just think we're going to divide it by the standard deviation. So what is that doing? What that's doing, it's going to give me the size of difference between my two means in standard deviation units. Note that this is kind of similar to the z-statistic or the z-score, where I looked at how far someone scored above or below the mean in standard deviation units. The z, if you recall, I took a person's score on x minus the mean, x bar, divided by SD, the standard deviation. So that got what's the size of difference between a person's score and the sample mean in standard deviation units. And here we're doing something different. We're saying what's the size of difference between two different means from two different groups, but we're still measuring it in standard deviation units. So at the bottom of the page here, I have a picture of two different distributions. Say this was a study where I was doing, say, treatments for depression. And I had one group was my treatment group and another group was my control group. And maybe I was measuring levels of happiness, hoping that my treatment group would be happier after treatment. So say this blue group, this blue distribution, maybe that's my control group. And I've drawn it like a normal distribution to make things easy for us. And so their mean is right here at 0. And these are the people that are one standard deviation above the mean in the control group. And here's two standard deviations above the mean in the control group. And then say my treatment group, after treatment, their level of happiness is right here. And so here's their treatment group. And so what I'm showing here is that the mean for the control group down here and the mean for the treatment group, the difference between those two means, they are 2 standard deviations apart from each other. Going from here, here's 1 standard deviation, here's 2 standard deviations. So the mean for the control group is 2 standard deviations lower than the mean for the treatment group. So I'm measuring the difference between my 2 groups in standard deviation units. And I do that with this formula. The mean for group 1 minus the mean for group 2, get the difference between the 2 means, divided by the standard deviation. So I measure that in standard deviation units. And so this picture shows a difference between 2 means of 2 standard deviation units. And so I would say the D in this example is equal to 2. This is showing you what a d-statistic of 2 looks like. If my effect size, if my d-statistic as an effect size is 2, it looks like this. This is the size of difference between the 2 groups. Now, if this was a treatment for depression, you could note a few things. There's clearly a difference. This control group is clearly lower than my treatment group. There's also a fair amount of overlap. There are some people who are in this treatment group, in this red group, some people down here that are actually overlapping with the blue group, and some people, there's a tail down here, there's a few people in my red group that are actually worse off than the average person in my control group. And in this blue group here, there's a few people in this blue tail right there, there's a few people in that blue tail that are actually better off than the average person who received treatment. So there's some overlap between these 2 groups. Now, one question I want to ask before I move on here is, when you look at this treatment size, what do you think about this? If I said I have this treatment for depression, and I did a study and calculated my effect size and got a D of 2, my D statistic was equal to 2, so that means I got an effect size that looks like this. There's 2 standard deviations of difference between these 2 groups. Would you be excited about this result, or would you be disappointed? Would you say, wow, this is incredible, fantastic, this is amazing, I really wonder if I knew someone who was depressed, or if I was depressed, or if I had a family member who was depressed, this is the treatment I would want to use. This is an incredible, fantastic treatment. Look at how big this effect size is. Or would you say, oh, I wish it was a little bigger. I wish we had something, where one group was here and the other group was like over here. They didn't even overlap, and there was like maybe 4, 5, 6 standard deviations of difference. Maybe you wish it was like that. Or maybe you're kind of in between. Well, you say, yeah, I wish it was a little better, but this is pretty good. So how do you feel about this treatment effect? Do you think this feels like an impressive treatment effect, or does this feel like kind of a small, you wish it was a little bit bigger? What do you think about a D statistic of 2? If that was the effect size for a treatment you were considering getting, how would you feel about that treatment? Now, I just asked you how you might feel if you were considering a treatment for yourself or for someone else, for someone you cared about, and the effect size for that treatment was a D statistic of 2. If the D statistic was equal to 2, would you be super excited, or would you be disappointed? Now, a different type of question is, well, how common would that effect size be in research? If we're doing research in psychology or neuroscience or testing effectiveness of treatments, how often might we do a study and get a D statistic of 2? Well, the answer there is that would be incredibly rare. That would be a huge effect size. We almost never ever get an effect size that big. And that leads us to another lesson, an important thing to learn in this course, is the fact that human beings are very complex critters. We human beings are very complex, and we're hard to predict. And so if we do any study trying to understand something important about human beings, if we're trying to understand the cause of different types of behavior, the cause of different disorders, or what makes people happy, if we're trying to determine the effectiveness of treatment, well, human beings are so complex, and there are so many different variables involved in determining outcomes to the important questions we want to address, that almost nothing we look at is going to produce a huge, amazing, whopping, gigantic effect size. In general, if someone were to do a study and they reported an effect size of 2, if they said, I did a study and I got a D statistic of 2, I would say one of 2 things probably happened here. Either A, you got an effect size that big because you made a mistake. There's some kind of mistake in your calculation. Or B, you're testing something that is not at all important or interesting. So, for example, I could do a study, for example, say I want to look at, say, a person's ability to solve algebra problems, and I get a sample of kindergartners and a sample of math majors at a university. And I give those two groups a test to measure their skills in solving algebra problems. And I might find a whopping gigantic effect size, a huge difference between those two groups. But that would not be an important, interesting question. It's like, well, of course there's going to be a huge difference between those two groups. So if you are looking at a topic that's really not very interesting, it might be possible to get a huge effect size. But if you're doing important research, addressing complex questions, we're never going to get an effect size this big. This is just unrealistic to get 2 standard deviations of difference between two groups is just a huge difference. We don't see stuff that big if we're addressing important questions about complex topics and trying to understand us human beings who are very complex critters. Jacob Cohen is someone who's done a lot of work on effect sizes. In fact, the d-statistic is something that's named after him. He's the one who developed, or he's the one who named it, I should say it, not named after it, but it's actually a lot of times people refer to it as Cohen's D. And Cohen suggested some cutoffs in terms of what we might call a small, medium, or large effect size based in general. These are arbitrary cutoffs. So some people really don't like the fact that he gave these cutoffs because they're just arbitrary values that he came up with. But they're really helpful, and I'm going to use them because I think it helps us keep in mind what types of effects we're looking at. And if we're not used to looking at research and interpreting effect sizes, it's really helpful to have some handles we can put on them to say, well, this effect size is small, and this one's medium, and this one's large. So if we calculate a d-statistic, and we get a D of 0.8 or larger, that is 0.8 of a standard deviation of difference between two groups or more, we're going to call that a large effect. And so that's nowhere near 2. Sometimes we might get a D of 1 or maybe a little slightly bigger than 1. That's really big. I've never seen a study doing something important getting a D of 2 standard deviations of difference. So 0.8 or larger, we'll call that a large effect. That's 0.8 of a standard deviation of difference between two groups or more would be called a large effect. If it's a half a standard deviation of difference, if your d-statistic is equal to 0.5 or larger, that's a half a standard deviation of difference between two groups or more, we'll call that a medium effect. If your d is 0.2 or larger, that's 0.2 of a standard deviation of difference between two groups or more, we'll call that a small effect. And if your d-statistic is less than 0.2, we'll call that, so small, we'll just call that a trivial effect. So those are some arbitrary cutoffs, and we'll be using these cutoffs to evaluate effect sizes in this course. And now we're ready for another song. Here is my song about the d-statistic. And the important thing to know about a d-statistic is that it tells you the size of difference between the means for two groups. And it tells you about the distance between the means for two groups, and this distance is measured in standard deviation units. So as the lyrics say, a d-stat says how far apart two means are split, measured with a standard deviation unit. So those are the lyrics for the d-statistic song. And my suggestion is always, I'll sing it through a few times in the video and maybe see if you can learn it the first time I sing it through and then sing along with me. And then before I'm done, see if you can sing along and sing all the words without looking at the words. So here is the song for the d-statistic.
Measured in a standard
So when I gave you the formula for the d-statistic, I said it was the difference between two means divided by something I called the pooled standard deviation. Now, up to this point, I've just been calling it the standard deviation, and I haven't clarified what I mean by a pooled standard deviation. And a pooled standard deviation is going to be very similar to simply taking the average of two standard deviations, a little different, but very similar to that. And the issue here is that if I have two groups, each group might have a different standard deviation. In fact, each group almost certainly will have at least a slightly different standard deviation. So if I have two groups and each group has a different standard deviation, which standard deviation should I use when I calculate my d-statistic? And the answer is I'm going to calculate a pooled standard deviation, which is going to be very similar to taking the average, except we're going to go back to the sums of squares level to do our averaging. So on this page, I have the formula that you would use to calculate a pooled standard deviation. And at the top of the page, I actually just review. This is just a review of the formula for a standard deviation. This is the same formula we looked at in Unit 1 when I gave you the formula for a standard deviation. We take the sum of squares, the sum of x minus x bar squared, and we divide that by n minus 1, which is our degrees of freedom, and then we take the square root, and that's our standard deviation. That's just a review of what we talked about before. And then right next to that, over here, I've just simplified that formula. Rather than writing sum of x minus x bar squared, I just write SS for sum of squares. And rather than writing n minus 1, I write df for degrees of freedom. So I can simplify my formula by simply saying the standard deviation, I simply take the square root of SS minus df. That is, take the square root of the sum of squares divided by the degrees of freedom. And so with that information, we can now use that format and calculate our pooled standard deviation. So what I'll do is I'll take the sum of squares for so if I have two groups, I'll take the sum of squares for my first group, sum of squares for group 1, and add to that the sum of squares for group 2. So I'll get the total sum of squares for both groups. And then I'll get the degrees of freedom for group 1, the size of group 1 minus 1, n minus 1 for group 1. And then I'll get the degrees of freedom, sample size minus 1 for group 2, and I'll add those two groups, those two degrees of freedom together. Or you could say it's the total sample size minus 2 would be another way of thinking of the same thing. And then I'll take my total sums of squares divided by my total degrees of freedom, and I'll take the square root of that. And this will give us something very, very similar to what we would get if I were to simply take the average of my two standard deviations. One thing this formula is doing is that it's actually weighting my two groups by their sample size. So if group 1 has a smaller sample, it's going to carry less weight in this formula. And if group 2 has a larger formula, it's going to carry more weight because I have my degrees of freedom, my sample size minus 1 in the denominators here. So that's going to, in effect, weight this by the sample sizes. So bigger groups will carry more weight, smaller groups will carry less weight, and I'm going back to my squared values to do my averaging rather than averaging across the unsquared values, or after I've taken the square root. So now if you were to just take the average of your two standard deviations, you should get something very, very close to your pooled standard deviation. In fact, if you get a pooled standard deviation, if you have one group has a standard deviation of 4 and another group has a standard deviation of 5, and you calculate a pooled standard deviation and get 4,682, you should know right away you've made a mistake. It can't possibly be that. If one group has a standard deviation of 4 and the other group has a standard deviation of 5, your pooled standard deviation needs to be somewhere in the middle between those. It should be about 4.5, somewhere between the two. So that's how you calculate a pooled standard deviation. And so to calculate your d-statistic, you would calculate the difference between two means, x bar 1 minus x bar 2, get a difference between two means, and then divide that by your pooled standard deviation. And that's how you calculate the d. Now, before we go on, I want to make you aware of the fact that the thing I'm calling a d-statistic, that is Cohen's d, is something that's essentially the same as what some people call a Hedges g statistic. Sometimes people make subtle distinctions between these two statistics, although these distinctions are often more confusing than helpful, and essentially they're the same thing. So I'm not going to be using two different terms in this class. I'm just going to be calling everything Cohen's d. I'm going to be calling everything a d-statistic. But if you read a journal article or you hear someone talking about Hedges G, or if you're doing a study and someone asks you to report Hedges G, know that it's essentially the same thing as a d-statistic. And here's a note, and this note is in your lecture notes, and you can read more about that if you want to learn about the difference between these two. Now, to have a good understanding of the meaning of different levels of a d-statistic, it would be good if you had examples of studies that produced different effect sizes. So what type of study might produce a very large effect? For example, like a d-statistic of 1. What type of study might produce a d-statistic of 0.6 or a d-statistic of 0.2, which would be a very small effect? So I'm going to give you some examples of different studies that produced different effect sizes, that produced different sizes of a d-statistic. And actually all my examples are going to be psychotherapy clinical trial examples. They're going to be studies where researchers are looking at a type of psychotherapy and they want to evaluate the effectiveness of that psychotherapy in treating some kind of psychological disorder or life problem. So they're all going to be psychotherapy clinical trials, which means they're going to be experiments where people are randomly assigned to a treatment group and a control group. And recall, if we're looking at an experiment or a clinical trial, this is the type of study where it's appropriate to report a d-statistic as our effect size. Because we have one dichotomous variable, people are assigned to a treatment group or a control group, so that's our dichotomous variable. And we have one numerically scaled variable, which is the outcome of the study. So if it's a treatment study looking at, say, treatment for depression, then depression would be the outcome, and it would be a numerically scaled variable. And again, the d-statistic will say, give us the information about what's the size of difference between the treatment group and the control group in standard deviation units. Now, actually, all the examples I'm going to give you, not only are they clinical trials, they're actually going to come from meta-analyses. So a meta-analysis is actually a combination of many studies together. So for example, if researchers have conducted several studies investigating a particular treatment for depression, we can look at the literature and all the results reported across those studies and average it together to say, on average, this is what the effect size is for this particular type of study. And so a meta-analysis is the results of several studies averaged together rather than the results of just one single study. So all the results I'm going to be showing you for my examples here will actually come from meta-analyses and not just from a single study. So as I go through this will be useful for giving you examples of different effect sizes. It also will give you some information about what types of life problems or psychological disorders are the ones that we can treat the best, which ones produce the biggest effect sizes, what types of psychotherapy produce the biggest effect sizes, and what are the disorders or life problems that are most difficult to treat? What are the ones that produce the smallest effect sizes? In fact, if you have some awareness of this, you might want to give a guess before we dive into the examples and see if you could guess. What do you think are the types of disorders or life problems that I'm going to show you that will produce the largest effect sizes, the ones that are easiest to treat or that we treat most effectively? And what would you guess are going to be the disorders or life problems that will produce the smallest effects, the ones that are most difficult to treat, that produce the smallest effect sizes? So let's take a look at some examples of studies producing different effect sizes. So when I perused the literature reporting meta-analysis results for clinical trials of different types of psychotherapy, the biggest effect size I could find was a study reporting a d-statistic of 1.0, a d of 1, which is a very large effect. And this was from a meta-analysis investigating the effectiveness of a treatment called prolonged exposure therapy that's a treatment for post-traumatic stress disorder. So post-traumatic stress disorder, or PTSD, that's sometimes people experience this after they've been exposed to a traumatic life event. For example, someone in the military who's been in combat, maybe a traumatic combat experience where people were killed, or if someone is a victim of sexual assault. So if people are victims of those types of traumatic life events, sometimes afterwards they experience post-traumatic stress disorder, which can involve feelings of anxiety. Sometimes it might involve nightmares. It might involve re-experiencing the trauma or problems in interpersonal relationships. And so a person named Edna Foa developed this procedure called prolonged exposure therapy for PTSD. And this involves gradually exposing the person so they can gradually approach their trauma-related memories and feelings and maybe situations. And this is one way that one method psychologists often use to treat fears or anxieties, because when we're afraid of something or anxious of something, we often want to avoid it. And when we avoid the things we're anxious of, that actually prolongs the anxiety and it keeps the fear going. And so one way to get rid of anxieties or fears is to approach and expose ourselves to the things that we're anxious of. So in this treatment, people expose themselves to their memories and their thoughts and their feelings of the traumatic event. And a series of 13 different clinical trials, so 13 different studies have been conducted testing the effectiveness of prolonged exposure therapy in treating post-traumatic stress disorder. And averaging across all these studies, the average effect size is a d-statistic of 1.0, which is a very large effect. Now, I might give a little bit of a caution here. I think this effect size might be a little bit inflated, because one thing I note, I mentioned that prolonged exposure therapy was developed by someone named Edna Foa, and I noticed that she is one of the authors on this meta-analysis. And I also know that most of these clinical trials were actually trials that were conducted in her lab. And usually when clinicians develop treatments and they test them, they often get a little bit better results than when other people test those treatments. It might be partly because the person who developed a treatment knows exactly how it's supposed to go. That person might be especially invested in doing everything right. So this d-statistic of 1.0 might be a little bit inflated. I would guess that if other research labs tested the effectiveness of prolonged exposure therapy, there's a good chance they might get slightly smaller results than this. And that's one of the things, that this was the largest effect size I could find, but this one actually might be a little bit inflated. So it's really, really hard to find a d-statistic this large, and even this one is a little bit questionable. So if the effect size for prolonged exposure therapy as a treatment for post-traumatic stress disorder, if that effect size is a d-statistic of 1, what exactly does that look like? How would you draw an illustration of a d-statistic that equals 1? How would you draw a picture of that effect size? It would be good if you could draw pictures of different effect sizes, or if you could at least recognize what properly drawn illustrations would look like. So let's do that. Let's draw a picture that would illustrate the effect size for the effects of prolonged exposure therapy as a treatment for post-traumatic stress disorder. And the first thing I'm going to do is I'm going to draw a bell-shaped curve to illustrate the distribution for the control group. And this would be the distribution on the outcome variable. So if this is a treatment for post-traumatic stress disorder that we're looking at, the outcome variable would be a measure of post-traumatic symptoms. And so, and for all these illustrations, we're just going to assume that our outcome variables are normally distributed. That will make things a lot easier for us. So I'm going to assume the outcomes variable is normally distributed, and I'll draw this bell-shaped curve here to indicate the distribution on this outcome variable for the control group. And I'll also put a line right down here, right down the middle. That line will represent the mean of the control group. So now that I've drawn this normal distribution of scores for the control group, I'm going to mark off and number the standard deviation units in this distribution. So I'm going to note the location of 1 standard deviation above the mean. So in a normal distribution, 1 standard deviation above the mean would fall right here. So I'm going to put a number 1 right there. And then right here, I'll circle there's 2 standard deviations above the mean. So I'll mark that, so I'll put a 2 at 2 standard deviations above the mean. And then I'll circle here's 3 standard deviations above the mean is right there. And then on the negative side, I'll circle there's -1, -2, and -3 standard deviations below the mean. And you should be able to recognize where these standard deviation units are located along a normal distribution. You should be able to recognize the location of 1 standard deviation above the mean or 1 standard deviation below the mean on a normal distribution. And you should be able to recognize the location of 2 standard deviations above or below the mean on a normal distribution. And I'll give you a few tips to help you recognize where these locations are. First, let's look at 3 standard deviations above the mean, right? I'll circle this. So 3 standard deviations above the mean. Note that if we look at our normal curve here, this line is curving down, and it's getting closer and closer to this x-axis, this bottom x-axis. And right at about 3 standard deviations above the mean, that's the spot where it looks like it's touching the x-axis. Now, technically, it never touches. If we look at the actual mathematical equation, our normal curve goes on infinitely in both directions, and it gets closer and closer and closer to this x-axis. It gets infinitely closer and closer, but it never actually touches. But when we draw a picture of it, it looks like it's touching right about 3 standard deviations above the mean. So if we're drawing a picture, just note that it's at the 3 standard deviations above the mean. That's the point where it looks like our curve touches the x-axis, even though it's not technically touching it. And let's see, here's the spot, I'll circle, here's the spot 2 standard deviations above the mean. One thing that might be helpful to note where this spot is to recall what you memorized before about area under the curve. Recall that 2% of the area under the curve is higher than 2 standard deviations above the mean, and 98% of the area under the curve is lower than that. That was one of those percentages that you memorized in our previous unit. So if just 2% of the area is higher than 2 standard deviations above the mean, then if I draw my line here at 2 standard deviations above the mean, I should get this little triangle, this little tail here. I'll circle, I'll kind of color it in here. This part I'm calling, that area I'm calling in should be about 2% of the area under the curve. It should be a fairly small little triangle there at this location of 2 standard deviations above the mean. You know, if I drew a line here and said, well, here's where I think 2 standard deviations above the mean is, if I drew my line there, clearly this is more than 2% of the area under the curve. So the location of 2 standard deviations above the mean should be a location where you get just this little kind of triangle there that's just 2% of the area under the curve. And how about the location of 1 standard deviation above the mean? Let's see, let's note, one thing to note is that if we look at our curved line here, the shape of the normal curve, it's kind of curving down, and then at some point it kind of flexes and changes direction and curves out. If I kind of exaggerate it, it's like it's curving down, and then it curves out. And right at the point, this middle point where it's changing direction is kind of right about the point where the 1 standard deviation above the mean is located. Or it's kind of halfway down this curve. If you're looking at it that way, it's the point where it crosses about halfway down that curve. Or another way to think about it, if you've clarified, here's where 3 standard deviations above the mean is, and here's where 2 standard deviations above the mean is, we should have it laid out so that there's an even distance between 0 and 1, 1 and 2, and 2 and 3. These should all be evenly spaced, and 1 standard deviation above the mean should be exactly halfway between 0 and 2. So those are some hints that you might be able to use to help recognize where these locations fall. So you should be able to recognize what does a normal curve look like, or be able to draw in general a normal distribution, the bell-shaped curve, and recognize where is 1 standard deviation above the mean, where is 2 standard deviations above the mean, and 3 standard deviations above the mean. So the next thing I'm going to do is to draw a line to indicate the mean of the treatment group. So I've already drawn the distribution of my control group, and I have the mean of my control group is right at 0. And so now I need to draw a line where the mean of the treatment group is going to go. And if I'm illustrating a d-statistic of 1, that means there's 1 standard deviation of difference between my treatment group and my control group. So the mean for the treatment group needs to be 1 standard deviation higher than my mean for my control group. So I'll go up here to 1 standard deviation above the mean, and I'll draw this red line here is right where the mean of the treatment group should go to illustrate a d-statistic of 1. And in my illustration, I'm also going to write the d-statistic value that I'm illustrating, and I'm going to also indicate whether I'm talking about a small, medium, or large effect using those cutoffs that I talked about before, Cohen's cutoffs for what is a cutoffs for a small, medium, large, and effect. And if you recall, I said that any d-statistic that's 0.8 or larger would be a large effect, so a d-statistic of 1 is clearly a large effect. So I'm going to write down here large effect. So I've drawn the line for the mean for my treatment group, and I've listed the size of my d-statistic. It's a d-statistic of 1, and I've listed that this is going to be a large effect. A d-statistic of 1 is illustrating a very large effect. Now we're simply going to draw the curve or the distribution of scores for the treatment group. And again, if we're looking at treatments for post-traumatic stress disorder, then the outcome variable will be a measure of post-traumatic stress symptoms. And we already drew the curve or the distribution of scores for our control group. That was the very first bell-shaped curve we drew. And so now we're simply going to draw a second bell-shaped curve, a normal distribution of the scores for our treatment group, the distribution of post-traumatic stress symptoms for our treatment group. And we're just going to assume that in both the treatment group and the control group, these symptoms are normally distributed. That will make things a lot easier for us if we just assume everything's normally distributed. And so I've already drawn the mean for my treatment group at the correct location. And now when I draw my bell-shaped curve, I simply draw an exactly same sized bell-shaped curve as I drew for my control group. So these two curves should be the same height. The point, if the mean for my treatment group is 1 standard deviation higher than the mean for my control group, then at the end here, the point where it looks like it touches the x-axis should be 1 standard deviation higher than the point where the control group looks like it touches the x-axis, and likewise down here at the bottom, the point where the control group looks like it touches the x-axis should be 1 standard deviation lower than where the treatment group looks like it touches the x-axis. So I've drawn two bell-shaped curves, and they should be exactly the same size, and the means of these two curves are exactly 1 standard deviation apart from each other, illustrating a d-statistic of 1. Now, one thing that's going to be super important here is to put some labels on my figure just to clarify what we're looking at. And one of the most important things to clarify is what is the direction of effect we're looking at here in terms of what direction means more PTSD symptoms and what direction means fewer PTSD symptoms. So I've been drawing my picture so that going to the left is more negative. That's having more PTS symptoms, and going into the right direction it would be more positive outcomes, having fewer PTSD symptoms. And actually, just to keep things consistent, I'm going to draw all my pictures of d-statistics this way, where going to the left is going to be more of the negative outcomes, and going to the right is going to be more of the positive outcomes. So I put a label here just to clarify that my scale at the bottom is intended to show that going towards the left is having higher PTSD symptoms. And I'm going to label the mean. So here I put a label here to clarify this is the mean for my control group, and I put a label here, this is the mean for the treatment group, the group that got that prolonged exposure therapy. And so now we can see that not only is there 1 standard deviation of difference between these two means, my picture now clarifies that the control group is having more PTSD symptoms because they're going more towards the left, and the prolonged exposure therapy is having fewer PTSD symptoms because their mean is going towards the right. Now, in addition to being able to draw a picture of a d-statistic and to illustrate what different effect sizes look like, it would be good to have ways that you can explain the meaning of effect sizes to people, and especially having ways of explaining the meaning of an effect size to people who maybe don't understand statistics very well. How would you explain an effect size to someone who maybe doesn't understand exactly what a standard deviation is? And this can be especially important if you're a clinical psychologist or if you're a medical practitioner, and if you give treatments to patients or to clients, because part of ethical practice means you have to gain informed consent before administering treatments. So how do you get informed consent if a client or a patient doesn't understand what the effect size is? Presumably, part of giving informed consent would involve knowing how effective the treatment is likely to be. So how can you convey information to a client or a patient that would explain how effective a treatment is likely to be if they don't understand for example, what a standard deviation is? So one option here is to use something called a common language effect size, sometimes abbreviated CL. And a common language effect size simply gives the probability of superiority. Stated in relatively plain language, it is the probability that if you receive this treatment, you will be better off than someone without treatment. More specifically, if I want to be more technical in my definition, I would say it's the probability that a randomly selected person from the treatment group will be better off than a randomly selected person from the control group. And we can actually calculate this probability by taking our d-statistic and multiplying it by the square root of 2. And if we assume that both of our distributions for the treatment group and the control group, if we assume that the distributions of scores on the outcome variable are normally distributed, and we've kind of been making that assumption all along here. If we make that assumption, then we can simply look up the probability of that value. So I take my d, multiply it by the square root of 2, and I get a value. Then I'll go to that normal unit table, that z table that gives probabilities of z-scores, and look up that value on that table and determine the probability of obtaining a score lower than that value from my z table. And that is my common language effect size. So let's take that, let's plug that in to our illustration of a d-statistic. And now here's a picture illustrating our d-statistic of 1, along with a blurb that I've plugged in at the bottom, giving information on the common language effect size. This is a kind of a blurb that maybe a clinician or a physician might be able to give to a patient or a client, giving them information on effect size. And it would be good if you could give this type of blurb. So if I said, here's a d-statistic of 1.0, it would be good if you could say, well, here's a blurb I could give a client or a patient explaining the meaning of this effect size. So it goes like this. I first say, with no treatment, your probability of superiority is 50%. Now, of course, that will always be true. If you don't receive any treatment, your probability of being better off than someone else who also receives no treatment is always just 50-50. You might be better, you might be worse, it's a 50-50 chance. So with no treatment, your probability of superiority is 50%. With treatment, your probability of superiority increases to 75%, which is an increase of 25%. So that's a blurb that you could give patients or clients on information about what this effect size means. Now, if you're wondering where I got these numbers, that's the process I just mentioned. I took my d-statistic and I divided it by the square root of 2. So if I'm looking at a d-statistic of 1, plug that in down here, 1 divided by the square root of 2, I get a value of 0.707. And then I went to a z-table, a normal unit z-table, and looked up the area under the curve below that point. That's the probability of getting a score lower than 0.707. And when I went to a z-table and looked that up, I got this common language effect size. It was precisely 0.76 is what I got, but I'm going to round that a bit because with this whole process, we're making approximations here. We're already making assumptions that our variables are normally distributed. They're probably not perfectly normally distributed. So we're making some approximations here. And because of that, I think we're much better off to use slightly rounded values that are easy to remember rather than trying to use super precise values that probably aren't quite that precise anyway. So I'm not going to use this precise 0.76. I'm going to round it to 0.75. And that's where I got this value here to plug in right over here, 75%. That's why I got that value. So I've got with no treatment, the probability of superiority is always going to be 50%. I calculated that with a d-statistic of 1, with treatment, that probability of superiority goes up to 75%. And so from 50% to 75%, that's an increase of 25%. So that's where I got those numbers from. And this is what an illustration can look like, all taken together here, illustrating what it looks like if we have a d-statistic of 1, how far apart these two means are split, and some information on the common language effect size at the bottom. So we've been looking at a d-statistic effect size of 1. What about a d-statistic of 0.8? This would be a little bit smaller, but still a large effect size. What's an example of something that we can treat that will produce a d-statistic of 0.8? Well, one good example of this is cognitive therapy for depression. And here I have an example from a meta-analysis that included quite a few studies. So this is a meta-analysis of 48 different clinical trials, 48 different studies testing the effectiveness of cognitive therapy for depression, 48 different clinical trials. And averaging across all these studies, they found that the effect size was a d-statistic of 0.8. There's 0.8 of a standard deviation of difference between the treatment group and the control group. And again, cognitive therapy for depression, that's that approach to therapy where people are taught to recognize the thinking patterns that they have that might be making them feel sad and depressed, and then developing methods for changing maladaptive thinking patterns. So if our d-statistic is 0.8, what does that look like? How would we illustrate a d-statistic of 0.8? And here is my picture illustrating the effectiveness of cognitive therapy as a treatment for depression. So again, these would be clinical trials where we have a control group that received no treatment and a treatment group that received cognitive therapy for depression. That would be our dichotomous variable. And then our numerically scaled outcome variable would be levels of depressive symptoms, the extent to which people are depressed. And again, I'm drawing my picture so that going to the left is going to be more negative outcomes, going to the right is going to be more positive outcomes. And so I've labeled it more depression symptoms is going to the left in my picture. And I have the mean for my control group, the distribution of depression scores for my control group. And I've labeled that the control group mean is right here. And for my control group, I've marked off the standard deviation units at the bottom, 0, 1, 2, and 3. I've marked off my standard deviation units. And then between 0 and 1, I've subdivided that. Actually, I went by 2/10 each. So this would be 2/10 and 4/10 and 6 and 8. So this would be 8/10 right here, where I've drawn that mean for my cognitive therapy group is 8/10 of a standard deviation higher than the mean for my control group. So I'm illustrating a d-statistic of 0.8. I've labeled it. 0.8 is still going to be a large effect. And then I have my blurb at the bottom giving information on that common language effect size, where I say with no treatment, your probability of superiority is 50%. And again, that will always be true no matter what. If no treatment, your probability of superiority is 50-50. And then here, with treatment, it increases to 70%. So when our d-statistic was 1, the probability of superiority was 75%. Now, when our d-statistic has dropped down to 0.8, this probability of superiority has dropped down to 70%. So with treatment, your probability of superiority increases to 70%, which is an increase, in this case, of 20%. So this is the illustration of what things look like for a d-statistic of 0.8. And cognitive therapy for depression is a type of treatment that produces a d-statistic of 0.8 that looks like this. So what about a d-statistic of 0.6? This would be dropping down to a medium effect size. What is something we can treat that will produce a d-statistic of 0.6? Well, one example of this is behavioral couple therapy for relationship distress. So this would be when a married couple or any couple is experiencing some kind of relationship distress. And behavioral couple therapy is a type of therapy where they're taught listening and speaking skills, things they can use to help them resolve conflicts. They're taught how to listen to each other, sometimes how to paraphrase each other before they take speaking turns, how to express their own thoughts and feelings and ideas to each other in ways that don't blame each other. And that would be behavioral couple therapy for relationship distress. And this meta-analysis is based on 30 clinical trials, so a fairly large number of studies have been conducted testing the effectiveness of behavioral couple therapy for relationship distress. And averaging across all these studies, this meta-analysis found that on average our d-statistic is 0.6. There's 0.6 of a standard deviation of difference between a treatment group that received behavioral couple therapy and a control group that didn't. And the outcome variable here would be levels of relationship distress, how much the therapy relieved the distress. So let's see what our illustration for a d-statistic of 0.6 looks like. So here is my illustration of a d-statistic of 0.6. So in this case, our outcome variable, the numerically scaled outcome variable, is levels of relationship distress. And again, I've set it up so that more distress is going to the left. It's a more negative outcome, and less distress or more relationship satisfaction would be going to the right. And we have our control group mean. The control group received no treatment, and there's our distribution of distress scores, that left bell-shaped curve. And our behavioral couple therapy, the treatment group that received behavioral couple therapy, that's that shaded bell-shaped curve on the right, is their distribution of distress scores. I've labeled this our d-statistic. We're looking at a d of 0.6, and I've labeled this now we're at a medium effect, because our d-statistic, recall that if your d-statistic is 0.5 or higher, we'll call that a medium effect. And this is higher than 0.5 but less than 0.8, so it's in the range that we'll call a medium effect size. And down here I have my standard deviation units I've marked off: 0, 1, 2, and 3. And now if I go between 0 and 1 standard deviations above the mean, I've marked that off again in units of 2/10. So here's 2/10, 4/10, and 6/10. So right at 6/10 a standard deviation, just slightly more than half a standard deviation above the mean, is where I've drawn the mean for my behavioral couples therapy group. And then down at the bottom, I have my blurb giving information on the common language effect size. So as always, with no treatment, your probability of superiority is 50%, like it always is. And with treatment, it increases to 65%. Notice, this might make it fairly easy to remember. Notice that our probability of superiority, as we're going from a d-statistic of 1 to 0.8 to 0.6, is actually dropping down by 5% each time. It kind of comes out nice and neat that way, which might make it kind of easy to remember. So with a d-statistic of 0.6, our probability of superiority is now at 65%. And 65% would be an increase of 15% over 50. So we go from 50% to 65%. That's an increase of 15%. So that is what our effect size looks like for behavioral couple therapy for relationship distress, and a d-statistic of 0.6. So what about a d-statistic of 0.4? Now we're dropping down into the range of a small effect size. So what is something that is relatively difficult to treat that will produce a d-statistic of only 0.4? Well, one example of this is dialectical behavior therapy for borderline personality disorder. So borderline personality disorder can involve someone having a lot of negative emotions, or maybe emotions that go up and down, and it often involves a fear of abandonment or difficulties trusting other people, and a history of having lots of unstable interpersonal relationships with people. Sometimes a person might swing back and forth between adoring and loving someone and then hating and being really angry with that person. And it can involve impulsive or sometimes dangerous types of behavior. And someone with borderline personality disorder might engage in self-harm behavior. That person might do things like maybe they're cutting themselves, or they might engage in suicide attempts. Now, dialectical behavior therapy is a treatment for borderline personality disorder that involves the therapist taking on a non-judgmental and accepting role towards the client. So the therapist expresses a non-judgmental acceptance towards the client, and the therapist teaches the client things like mindfulness, which involves being able to accept and live in the current moment. And the therapist teaches the client skills for distress tolerance and skills for emotion regulation. So that's dialectical behavior therapy for borderline personality disorder. Now, there haven't been a whole lot of studies testing this treatment, but there have been. This one meta-analysis I found here is a meta-analysis that found 8 separate studies, 8 different clinical trials testing dialectical behavior therapy for borderline personality disorder. And the average d-statistic across those 8 clinical trials was a d-statistic of 0.4, which would be a small effect. And what that illustrates is that borderline personality disorder is a relatively difficult type of disorder to treat. So what does our illustration of a d-statistic of 0.4 look like? And here is my illustration of a d-statistic of 0.4, illustrating the effectiveness of dialectical behavior therapy as a treatment for borderline personality disorder. So again, we're looking at clinical trials where there's a control group that received no treatment and a treatment group that received dialectical behavior therapy. And one of the key symptoms, one of the key problems with people who have borderline personality disorder would be suicidal behavior. So here I have the key outcome variable is looking at extent of suicidal behavior, and going towards the left is going to be more suicidal behavior, and going to the right is going to be the more positive outcome with less suicidal behavior. And I have my distribution of suicidal behavior in the control group, which is the bell-shaped curve on the left, and the distribution of suicidal behavior in the treatment group, which is the bell-shaped curve on the right. And then I've marked off my standard deviation units. I put 0 right at the mean for my control group and marked off 1, 2, and 3 standard deviations above the mean. And then I've marked off in between 0 and 1 standard deviations above the mean. I've marked off 2/10 and 4/10. So right about 4/10 above the mean of the control group is where I drew the mean for my treatment group. That's not quite halfway between 0 and 1, not quite half, a little less than half a standard deviation of difference between my control group and my treatment group. And so this is a d-statistic of 0.4, and I've clarified, I wrote the label here, this is a small effect size now, because anything between 0.2 and 0.5 is what we would label a small effect. And then down at the bottom, I have my blurb that we could give to someone to give the common language effect size information. So as always, with no treatment, your probability of superiority is 50%. And with treatment, it increases to 60% now. So for a d-statistic of 0.4, the probability of superiority is 60%. And so going from 50% to 60% is an increase of 10%. And we're continue to follow that pattern. Each example is actually dropping down by 5%, you might notice. So this is a picture of illustrating the effects of dialectical behavior therapy as a treatment for borderline personality disorder, illustrating an effect size of a d-statistic of 0.4. And finally, what about a d-statistic of 0.2? This would be a very small effect. So what's an example of something that is very difficult to treat that produces a d-statistic of only 0.2? Well, one example of this would be cognitive behavior therapy with something called motivational interviewing for treating alcohol use disorder, which is just a formal name for what people often call alcoholism or alcohol dependence. And issues regarding alcohol use and actually any type of chemical dependency, these types of issues can be very difficult to treat. And part of the reason for this is, well, for one thing, it's just simply very difficult to overcome a physical addiction. And also, people with these disorders, if they have an alcohol use problem or problems with chemical dependency, people with these problems oftentimes don't think they have a problem, or they don't really want to change, or they're not sure they want to change. So motivational interviewing is a method for trying to move people towards considering the possibility of taking steps towards making a change. With motivational interviewing, a therapist would take a non-judgmental, accepting attitude towards a client, and a therapist might ask questions, engage in kind of an interview. It's an interview that's intended to try to motivate the client towards making a change. So the therapist would have a process of asking questions and interviewing the client that encourages the client, for example, to consider both the advantages and the disadvantages of making a change. And the therapist would show understanding when the client talks about reasons for not wanting to change. And the therapist would follow up with interest when a client mentions a possible reason why that client might want to change. So that would be motivational interviewing for treating alcohol use disorder. And this meta-analysis here that I found has 9 clinical trials, 9 different studies looking at the effectiveness of motivational interviewing for treating alcohol use disorder. And averaging across these studies, the d-statistic was only 0.2. 2/10 of a standard deviation of difference between the treatment group and the control group in their use of alcohol. which is a very small effect, and that illustrates the extent to which alcohol use disorder can be a very difficult disorder to treat, especially if you're dealing with people that aren't sure they even have a problem and not sure they want to change. So what does a d-statistic of 0.2 look like? And here is my picture illustrating a d-statistic of 0.2, illustrating the effectiveness of motivational interviewing as a treatment for alcohol use disorder. So we have a control group that received no treatment and a treatment group that received motivational interviewing. And our outcome variable is levels of alcohol use, how much the person is drinking. And as I've been doing all along here, going towards the left is more problematic behavior. So that would be more alcohol use, and going towards the right is less alcohol use. And the bell-shaped curve on the left is the curve for our control group, showing their alcohol use levels on the outcome variable, levels of alcohol use for our control group. And then the bell curve on the right is the distribution of alcohol use levels for our treatment group. And you see these two bell-shaped curves are almost entirely overlapping at this point. So we're now down to a very small effect, a d-statistic of 0.2, and our two distributions are almost right on top of each other. So down at the bottom, I've marked off my standard deviation units, and we see that our treatment group is just 0.2, just a little bit higher than our control. There's not much difference between our treatment group and our control group. Our treatment group mean is just 0.2 of a standard deviation higher than the mean for our control group. And then down at the bottom, I have the blurb that gives information on our common language effect size. So I say with no treatment, your probability of superiority is 50%, as always. With treatment, it increases to 55%. So now we're down just to with a d-statistic of 0.2, our probability of superiority is just down to a 55% now, which is an increase of 5%. Going from 50% to 55% is an increase of just 5%. So that's what a d-statistic of 0.2 looks like, the effectiveness of motivational interviewing as a treatment for alcohol use disorder. And that is everything for Part A of Unit 2.